Warahmatullahi ta'ala wabarakatuh. Today I'm going to share with you the example for simply supported rectangular beam. Given here is structure layout plan for simply supported rectangular beam. So how do we know this layout is simply supported rectangular beam? So we know that all of the area here is a void where the beam is not connected to the slab. Therefore, the beam is considered as a rectangular beam. So I can consider, because this beam is connected with two column here, this beam is called as a simply supported beam. This is also a simply supported beam. So today we are going to design beam AC2. So this beam is AC2. This beam AC2 is connected to secondary beam B12. Therefore, we need to know and understand how we're going to transfer load from this secondary beam to this primary beam. Given here is the data that we need for the design. So given the characteristic strength of the concrete is 30 Newton per millimeter square. Characteristic strength of steel is 500 Newton per millimeter square. Diameter bar assumption for the initial assumption is 16 millimeter. Diameter link is 8 millimeter. Fire resistant 1 hour. Exposure class is XC1. The brick wall on each of the beam that we have here is 26 kilonewton per meter cube, which is its unit weight. Height of the brick wall that is connected to this beam is 3 meter, and the thickness of the brick wall is 115 millimeter. So we did this information in order for us to calculate the self-weight of the brick wall. The variable action given here is 6 kilonewton per meter on each of the beam. The beam size is 200 millimeter times 400 millimeter, and the structural class is S4. In order for us to solve this problem, the first step or the first things that we have to do is to calculate the nominal cover. In order for us to calculate the nominal cover, we have to compare in three different conditions. The first one is due to the fire resistance, second one is due to the bond requirement, and the third one due to the exposure class. The basic formula for the C nominal can be referred to clause 4.4.1, which is C nominal equal to C minimum plus C deviation. So the first condition is due to the fire resistance. We know that the fire resistance given here is a 1 hour. So the formula to calculate the C minimum due to the fire resistance is equal to alpha SD minus diameter link minus diameter bar over 2. The alpha SD is equal to alpha plus 10. How to determine alpha? We can determine alpha by referring table 5.5 for simply supported beam. Then we refer the R60 with a B of 200 millimeter. Therefore, we can determine the alpha value is 30. Then we can substitute this value in this formula. C minimum is equal to 30 plus 10 minus 8 mm diameter link and 16 over 2 for the diameter bar over 2. Then we get the answer for C minimum due to the fire resistance is 24 millimeter. Second one, okay, we have to calculate due to the bond requirement. So the bond requirement, we can refer to table 4.2. So in our case, we use a separated. So therefore, the C minimum B for the separated one is equal to diameter bar, where the assumption of the diameter bar is 16 mm. Therefore, C minimum B is 16 mm. The last one is due to the exposure class, due to the environmental exposure. So we refer to the exposure class, which is XC1 given in the question here. Then we refer to table 4.3N, the strength class. So in our case here, the FCK given is 30 Newton per millimeter square. Therefore, in this case, the condition says that if the FCK is more or equal to 30 Newton per millimeter squared and above, we have to reduce the class by 1. Therefore, by referring table 4.4N, we know that the structural class given here is S4. We have to reduce by 1. Therefore, the structure class become S3. That's why the C minimum durability is 10 mm. Then we compare this C minimum durability, C minimum B, and C minimum due to the fire resistance. Which one is the biggest one? So this based on these three conditions, we know that the highest C minimum is due to the fire resistance, which is 24 mm. Therefore, C nominal is equal to C minimum plus C deviation. 24 plus 10 mm, we get 34 mm. So the deviation is referred to clause 4.4.1.3, which is 10 mm. Therefore, the answer here is 34 mm. We have to round up into the nearest biggest 5, which is 35 mm. Second step, which is the design action. So on the design action, we have to understand the condition of the beam. We know that this beam is connected to secondary beam B12, where we have to transfer load from this secondary beam to the primary beam. Therefore, we have to analyze the secondary beam first. That's why in this calculation here, so we have to draw the free body diagram for the secondary beam B12B, which is 3 meter length. So here is the calculation for the permanent action and also variable action, where the beam self-weight is 25 times 0.2 times 0.45, we get 2.25 kilonewton per meter. The brick wall is equal to 26 times 0.115 times 3 meter high, which is equal to 8.97 kilonewton per meter. Then the total permanent action is 11.22 kilonewton per meter. The given total of variable action is 6 kilonewton per meter. Then we factorize the load or action, N equal to 1.35 GK plus 1.5 QK. Therefore, the answer here is 24.15 kilonewton per meter. This is how we're going to transfer load from beam B12 to beam 2AC. We have to find the reaction at point 1 and also point 2. Become a point load on top of primary beam 2AC. So P is equal to WL over 2. Then the answer here, the reaction is 36.23 kilonewton. Then, next step, we have to analyze the primary beam here. We draw the free body diagram of the primary beam here, which is 5 meter AC2. Then, this beam is receive a point load from the secondary beam P equal to 36.23 kilonewton. Then we have to find the uniformly distributed load on top of this beam B2AC. Same process what we have done before. So the permanent action, the total of the permanent action is 11.22 kilonewton per meter, and then the total variable action is 6 kilonewton per meter. We factorize the load, we get 24.15 kilonewton. Next process, we have to draw the shear force and also bending moment, because we need to know the maximum shear force and the maximum bending moment in order for us to design the main reinforcement and also shear reinforcement. After we get all those action acting on top of this primary beam, so we have to calculate the reaction of the primary beams. Therefore, the reaction from the point load P over 2 and then the reaction from the uniformly distributed load is WL over 2. We get the answer here, 78.50 kilonewton. Okay, so here is the shortest way how we can draw the shear force diagram. Okay, so we know that the first point reaction here is 78.50 kilonewton. Okay, and then we have to find the value at point 2. Okay, we know that the value of the reaction here is 78.5. Sorry, this is typo. Then we have to minus with 24.15, which is uniformly distributed load on top of the beam time with the distance of this length, which is 2.5 meter. We get the answer is 18.125 kilonewton. Then we have to find the shear force at point 3. So how we going to determine this? By minus, okay, 18.125 minus with 36.25. 36.25 is the point load due to the secondary beam here. That's why it minus here, because the action is acting downward. Then we get the answer minus 18.125. Then at point 4, we get from this value, negative 18.124, we have to minus with uniformly distributed load. Then we get the answer negative 78.5. Then we close the loop. How to draw or determine the bending moment diagram? So this is the shortest way. So in this case, okay, we can use this analogy or this method or this concept. So the maximum moment of this beam is equal to area of the shear force. Therefore, it's equal to half time 2.5, which is the distance of this shear force, and then time with 78.5 plus 18.125, because this is a trapezoidal. Then we get the answer of the maximum moment is equal to 120.78 kilonewton meter. The next process is design the main reinforcement. Okay. To design the main reinforcement, the first step we have to know the section of the beam. So we should know every single element in this beam. So this is the height of the beam. This is the effective depth of the beam. This is C nominal. This is diameter length plus diameter bar over 2. So in order for you to determine the effective depth, the formula is the height of the beam minus with the nominal cover minus diameter length minus diameter bar over 2. Therefore, we get the answer here, 399 millimeter. So the nominal cover is based on the nominal cover that we have calculated before. The first one, we have to calculate K. So K is equal to M, which is the maximum moment, over the FCK, which is characteristic strength of concrete, time B, which is BW here, and time with the D. Therefore, it equal to 120.78 times 10 power of 6 over 30 times 200 times 399 power of 2. We get this answer 0.126 less than 0.167. And the conclusion here, compression reinforcement is not required. The beam is considered as singly reinforced. When we get the answer, K value here is more than 0.167, means that it's more than K balance, the compression reinforcement is required. Therefore, the beam that we have to design is doubly reinforced, means that we have to design the reinforcement for the tension and also compression. So in this case, because this is a singly reinforced, we only design the tension reinforcement at the bottom of the beam. Then we provide the minimum numbers of the reinforcement for the top as for the compression. Then we have to calculate the lever arm, which is the distance of Z, which is equal to D times 0.5 plus 0.25 minus K over 1.134 square root. Then we get the answer here, 0.87D. We have to compare this value with 0.95D. 95D is the limitation. So if you get the answer is more than 0.95D, you have to use Z as 0.95D. In my case here, when I do calculate the Z value, I got the answer 0.87D. That's why I use 0.87D as the Z value. Then we have to calculate AS. What is AS? AS is area of tension reinforcement required for the beam that we refer. So the formula is equal to M over 0.87 FYKZ. Then we calculate here, we enter, substitute all those values here, we get the answer of AS required here. So by referring dimension table at the back of your design appendix, you may provide the area provided here, okay, should be higher than AS required here, and it should not be too big, and it should be in a balanced condition. So in my case here, so my AS required is 799.86. That's why I provide here 804 millimeters square. Then the numbers of the reinforcement is 4H60. Here is the condition that you have to know. The minimum numbers of the reinforcement for beam is actually 2. One for the left, one for the right. And then the minimum diameter bar is 12 mm. That is normally that we practice as an engineer. But sometimes we prefer 10, but normally it is a 12. It depends on the needs of the design. The maximum numbers in my preference is 6 numbers. Because, so when we have a 6 number, we can have the maximum spacing of the bar is a 2 spacing. So in this case, we may control the cracking of the beam. So if not, we can have more spacing if the BW is bigger. So it will not fail due to the crack. So we have to control the arrangement of the reinforcement. Either we would like to have one spacing between the bar, or two spacing, or three spacing. It can be 8, it's up to you. So as long as every single element that we have to check is passed. After we determine the AS, what we call it AS provided, we have to compare this value with AS minimum and AS maximum. So AS minimum, we can refer to clause 9.2.1.1 using this formula 0.26 FCTM BTD over FYK should be compared with 0.013 BTD. So the FCTM value is referred to table 3.1. So you check the FCK value given in your question or in your solution, which is 30 Newton per millimeter squared. That's why my FCTM here is 2.9. So by comparing this value, I get the answer by using this formula. The value is bigger than 0.013 BTD. That's why I use AS minimum, the biggest one, so 1 to 0.34. AS minimum is 0.04 AC. This is the formula, equal to 0.04 B times H, which is 3,600. Then we made a conclusion. Here, AS minimum should be less than AS provided and less than AS maximum, where the AS provided that we provide here for the main reinforcement should be in between AS minimum and also AS maximum. Here, I'm going to share with you what happened if your AS provided is bigger than AS maximum. It means the section capacity is insufficient. Therefore, the load that you apply to the beam is bigger than the section cannot cater the maximum. So what you have to do, you have to redesign the section by providing extra size, which means you have to increase the size, either it's a BW or the high, in order for you to increase the AS maximum here. So in this case, you have to redesign the section. Next process is design shear reinforcement. So what is shear reinforcement? Shear reinforcement is actually shearing for the purpose to tighten up the main reinforcement of the beam. So we have to know that shear reinforcement is the important part for us to make sure that this structure is not failed due to the shear failure. So we know that this VED is equal to V maximum. We get from the shear force diagram, which is 78.5 kilonewton. The first step, we have to compare VED with VRDC or Vmin. So we have to calculate VRDC and also Vmin. We compare which value is bigger, then we compare with VED. So VRDC is equal to 0.12 K times 100 times rho 1 FCK power of 1/3 and BWD. So to calculate K, K is equal to 1 plus 200 over D, and this value should be less than 2 millimeter. So if you get the answer is more than 2 millimeter, therefore the K value that you should use in the formula is 2 millimeter. Same goes to rho 1 is equal to ASL. ASL is area of tension reinforcement provided divided by BWD. So you should compare with 0.02. If you get the value is more than 0.02, you have to use rho 1 as 0.02. So for the V minimum is equal to 0.035 K power of 3 over 2 FCK power of 1 over 2 BWD, then we get the answer. So by comparing VRDC and Vmin, the biggest value is VRDC. That's why I compare VED with VRDC, and then the answer is shear reinforcement is required. So we have to calculate the VRD max in order for know that we have to design the shearing or not, or we have to provide the minimum. So VRD max is equal to 0.36 BWD times 1 minus FCK over 250 times FCK over cotangent theta plus tangent theta. So cotangent theta is equal to 1 over tangent theta. For the first one here, to calculate the VRD max, so we have to use theta is equal to 22 degree. So we get the answer 263.42 kilonewton. Then we compare VED with VRD max, we get less. Therefore, we design shearing. So what happened if we get the VED is more than VRD max? we have to use this formula and changing the theta here with 45 degree. Then if we get this condition, VED less VRD max, then we can design the shear link same as this one. What happened if after we change the theta into 45 degree, the answer is still same where VED is more than VRD max? We have to calculate the new theta by using the formula given in the design appendix. You may refer to the design appendix given. So, then if you get the answer VED less than VRD max, then you design the shear link. If you get more than VRD max also, still get the same answer, means that you have to redesign the section. So means that it failed due to the shear. So in this case, the answer is VED is less than VRD max. Therefore, we have to design the shear link. So to design the shear link, we have to provide the ratio of ASW over S. This is a ratio of the link stirrup. So equal to VED over 0.78 FYK d cotangent theta. I got the answer 0.204 here. Then refer the dimension table, the last one for this stirrup. Then I provide H8 300. H8 is the dimension of the diameter link, which is the minimum, which is 8 mm. And then 300 is the distance between the link, the first link and the second link and the third link, which is 300 center to center. The value is 0.335, is bigger than 0.204. Then, next step, we have to calculate the deflection check. What is deflection check? Deflection check is fall into serviceability limit state design, where the serviceability limit state design, we have to check deflection and also cracking check. So what is deflection? So deflection happen when we apply the load, then we have the bending behavior. So in this bending behavior, we have to make sure that it's not exceeding the maximum deflection. So we have to check the actual deflection and also the maximum deflection. The actual deflection should not be more than the maximum deflection. So that's why we have to make sure the beam is passed due to the deflection. So in order for us to calculate the deflection check, we have to calculate this rho is more than rho naught or rho less than rho naught, which equation that we have to use in order for us to calculate L over D basic. If we get rho more than rho naught, the equation 7.16b is applied for this calculation. So if we get rho less than rho naught, the equation 7.16a is applied for the calculation. So in order for you to calculate rho is equal to AS required over BWD, which is, this is the answer. Rho naught is equal to square root FCK times 10 power of minus 3. Then you get this answer. So based on this answer, I get this L over D basic is equal to 15.52. Here I'm going to tell you that how to determine this K. K is referred to table 7.4, and because of this beam is a simply supported beam, that's why the K value is equal to 1. And another thing is you have to understand this rho prime. Okay, because of we are using 7.16b, there is formula here or symbol here rho naught. So in this calculation, we consider rho naught is equal to 0 because this beam is singly reinforced. It's not doubly reinforced. There are no AS prime, which is area of the compression reinforcement. Okay, so we consider rho naught is equal to 0. Then L over the actual is equal to L over the basic time modification factor of the reinforcement time with the modification factor of the span. So the modification factor of the reinforcement is equal to AS required, AS provided over AS required. So the modification factor of the span is equal to 1 in this condition because of the span length is less than 7 meter is equal to 1. If it's more than 7 meter, so we have to use this ratio with 7 over L effective. So if L effective, for example, 8 meter is 7 over 8, you will get the answer here. And then the last one is L over D actual. So you have to calculate L over D actual here. So your L is the length of the beam. So length of the beam is 5,000 millimeter divided by D, which is 399. So therefore 12.53. Then we made a conclusion L over the actual is less than L over the allowable. Therefore the deflection check is passed. Next is the last check for the serviceability, which is the cracking check. So we have to draw this section in order for us to know how many spacing that we need for the reinforcement arrangement. In my case here, I'm providing 4H16. Therefore, I arrange my reinforcement here double 2 reinforcement at the left, 2 reinforcement at the right. Therefore, I only have one spacing here. You may arrange your reinforcement, for example, 1, 2, 3, 4 here. Then you have 3 spacing. But you have to make sure, when you have a 3 spacing, you have to make sure that the spacing is more than the minimum, which is 25 millimeter. Assume that the WK here I'm using is 0.3 millimeter. So the first step, you have to calculate the steel stress. So in my formula here, so the steel stress formula is FYK time with GK plus 0.3 QK over 1.15 time 1.35 GK plus 1.5 QK. So here, the total GK, you have to total up secondary beam and also primary beam. Same goes to QK. Then you get the answer here. The steel stress is 234. How to determine this maximum spacing of the reinforcement? So the maximum spacing is referred to table 7.3N, and we have to refer WK is equal to 0.3 mm. So we do the interpolation. I get the S maximum is equal to 207.5 millimeter. Then the actual spacing is equal to BW minus 2C nominal left and right minus 2 diameter link left and right and minus 2 diameter bar, because I do arrange my reinforcement like this 1, 2. So if you arrange 1, 2, 3, 4, you will minus with 4 diameter bar and you have 3 spacing here. In my case, I only have 1 spacing. So the answer is 77 mm. Then I made a conclusion. S minimum, which is the aggregate maximum size, 25 mm, less than S actual 77 millimeter and less than S maximum 207.5. Therefore, the crack check pass. Last but not least is the reinforcement detailing. We have to draw the detailing of the reinforcement for the beam longitudinal section and also cross section. So on the longitudinal section, so here is the bottom reinforcement where it is a tension reinforcement. This is the hanger bar. So we provide based on the minimum, AS minimum to H12. This is 4H16. Then this is H8, the 100 center to center is the link. Here is the cross section. We cut the section here, and then we get this section of the beam, which is 4H16 at the bottom to H12, which is hanger bar, which is we not design it, we provide based on the minimum area required. And then this is the link H8 300 center to center. I do hope based on my explanation on simply supported rectangular beam, you understand how to design simply supported beam rectangular. So I hope if you have any question, you may come and see me and text me or WhatsApp me for the further discussion. That's it. Thank you.